Welcome to lecture number 22. This is, sadly enough, already the last and final lecture in this course. We have some unfinished business from the previous lecture. In the previous lecture, I proved a very abstract splitting result, some strong hypothesis under which the unreduced suspension spectrum of an orthogonal space splits into pieces that are the subquotients in the skeleton filtration. Here's the statement again. We need a flat orthogonal space. And then we have to assume that the projection map from the value at r to the m down to the value at r to the m modulo the mth latching object admits a section, but only in the OM equivariant genuine stable homotopy category. Then we've used some adjointness tricks to turn those sections into morphisms sigma n, which go from this subquotient in the skeleton filtration induced up all the way to an orthogonal spectrum. We take the wedge over all these together, and that provides a stable global splitting of the unreduced suspension spectrum of X, so an isomorphism in the global stable homotopy category of this object with a wedge or sum of things coming from the subquotients. As I already mentioned a number of times in the previous lecture, I would like to apply this to provide a stable splitting of the orthogonal space that are called boldface O, which is made from the orthogonal groups. Let me briefly recall the relevant definitions. O of V is the orthogonal group of V. V is some inner product space. And the structure map phi lower star from O of V to O of W for a linear isometric embedding phi from V to W is given by conjugation by phi and the identity on the orthogonal complement of the image. And altogether this gives us an orthogonal space. We also analyzed the latching map. The nth latching map from Lm of O to the value of O at r to the m is a closed embedding. With image the following subspace of the orthogonal group O of m, those A in O of m such that the kernel of A minus em, so this is the m by m identity matrix, is non-zero. Equivalently, these are those matrices that have +1 as an eigenvalue. This map is not just a closed embedding and it's automatically OM equivariant. I will omit the fact that it's even an OM equivariant cofibration, and this then verifies that the orthogonal space O is actually a flat orthogonal space. So we have verified the first hypothesis of this general theorem, but this is really only a technical hypothesis. The much more serious hypothesis is these splittings, and that's what I'm going to come to next. Before I get to those splittings, I want to first give you a different interpretation of what the subquotient of the skeleton filtration looks like in the case of the orthogonal groups. And I claim that it's homeomorphic to the one-point compactification of the adjoint representation. So let me recall the adjoint representation of OM is, well, formally it would be the tangent space at the identity with the OM action given by differentiating the conjugation action, but we want to use this more concrete description at M just as the skew symmetric matrices. So these are M by M real matrices with the property that the transpose is minus the matrix, so they are skew symmetric. And now the next aim is to give an isomorphism of base OM spaces between OM at modulo Lm of O with a one-point compactification of at M. This is an isomorphism, homeomorphism of base OM spaces. I'm going to use this notation OM to the odd to emphasize which action of OM on this space we're considering. Namely, we're considering the conjugation action or the adjoint action, not the left or right translation action. Add indicates that OM is acting on itself by conjugation. This homeomorphism is a classical fact, and you can find it, for example, in Miller's paper on the subject, on the stable splittings of Stiefel manifolds. We need a particularly equivariant, a particularly symmetric version of this identification, and this I am taking from a paper by Crabb, which is written in a very nice and very invariant way so that everything can be adapted with the right amount of equivariance that we need. The identification of the subquotient of the skeleton filtration of O with the one-point compactification of the adjoint representation is only linear algebra. The key ingredient is the following lemma. A certain map, namely the Calyey transform, this is a map that I write Cm. It goes from this vector space, the underlying vector space of the adjoint representation, to the mth orthogonal group, and I want to emphasize that here we have the conjugation action. The map sends a skew-symmetric matrix to the following expression: x minus the m times m identity matrix composed with x plus the m times m identity matrix to the minus 1. This map, I claim, is an OM equivariant, open embedding onto the open subset that is exactly the complement of the Lecce space. Equivariance refers to conjugation action on both sides, and this is the easiest part. I won't even bother to prove anything about it, that this map is compatible with the conjugation action of the orthogonal group on both sides. Here's the proof, or at least various important steps in the proof. The first thing is to convince yourself that this actually is a meaningful expression. So in particular, x plus the m by m identity matrix is actually invertible. So this is the first thing I want to explain. For all x in ad m, so skew symmetric, x plus em is invertible. And this follows from the fact that minus 1 is not an eigenvalue of x, because if minus 1 is not an eigenvalue, then this matrix has a trivial kernel, and hence it must be invertible. So why is minus 1 not an eigenvalue? So let's show this. Suppose we have a vector in R to the m, which is an eigenvalue, is such that x times v is minus v. And then we do a bunch of elementary calculations with matrices. We can take the transpose of v, matrix product with v, so this is also the norm v squared. Because of the assumption that minus 1 is an eigenvalue of x, this is minus v transpose times x times v. Now we can use the fact that x is in ad m, so x is skew symmetric, so that means we can replace this minus sign and the x by x transpose, so this is v transpose x transpose v. Transpose is anti-multiplicative, so this is xv in parentheses transpose times v, and now x times v is minus v, so this is minus v transpose v, so this is minus the norm v squared. So altogether we conclude that v squared is minus the norm v squared, so this implies that v has to have been 0. In other words, there is no eigenvector for the eigenvalue minus 1, and so this matrix is indeed invertible, and this expression makes sense. Well, it makes sense in the matrix ring, but the next claim that we have to verify is that it actually lies in the orthogonal group. So this is part B. We have to show that for all x in ad m, the matrix we write up there, x minus em times x plus em inverse lies in the orthogonal group in O of m. So this again is a relatively elementary calculation, so let me show you how it goes. Being in the orthogonal group means that the product of this and its transpose is the identity matrix, product on both sides. I will only give you one of the two products, the other one is similar. So let me take this matrix to the transpose, so x minus em times x plus em inverse transpose, then multiply it with this matrix, x minus em times x plus em to the inverse, and now we're going to analyze this expression. So transpose is an anti-automorphism, so I can put it through by interchanging the order, and I can put it through the inverse. So this will be x transpose plus em inverse times x transpose minus em times x minus em times x plus em inverse. Now I'm going to use the assumption that x comes from the adjoint representation. In other words, it's skew symmetric. So I can put a minus sign here. So this is minus x plus em inverse times minus x minus em times x minus em times x plus em inverse. The next observation is that these two matrices, while they are different, these two matrices commute. So I can interchange the order in which I'm doing this. Let's do this. So this is minus x plus em inverse times x minus em times minus x minus em times x plus em minus 1. And then again we just look at it. So this matrix, and here's the inverse up to the minus sign. So this is minus em. And then also here, these are inverses to each other except for the minus sign in here. So this is also minus em. And altogether we conclude that this is the n by m identity matrix. In other words, we have verified that the expression here really is an element of the mth orthogonal group. We know now that this formula is really meaningful, that it does indeed send a skew-symmetric matrix to an element of the orthogonal group. And now I want to give you the inverse. I will now define a map in the other direction, but only defined on this open subspace. This is part C. So we consider a matrix A in OM without Lm of O. These were the matrices that have +1 as an eigenvalue, so this matrix does not have eigenvalue 1. So +1 is not an eigenvalue of the matrix A, and that means that the matrix Em minus A is invertible. So we can form a similarly looking expression as up here, and I claim that we land in the adjoint representation. So I claim that this expression, Em minus A, now the inverse is on the left, composed with Em plus A, lies in at M. This one more time is an elementary calculation, manipulation with matrices. Let's do this. Also, mainly to convince you that it's elementary and that there's nothing deep hidden in here. The hypothesis that A is an orthogonal matrix means that A times A transpose, and also the other way around, A transpose times A, are both the M by M identity matrix. Hence we can expand Em plus A times Em minus A transpose to A minus A transpose, and this is the same as minus Em minus A times Em plus A transpose. Now we take this equation, multiply it from the left with the inverse of Em minus A, and from the right with the inverse of EM minus A transpose. And then we get this relation. On the right-hand side, we pull the transpose out, and then we use that transpose is anti-multiplicative. Now altogether we have exactly shown that the matrix under consideration is sent to its negative when we transpose it. Our final claim is that the Cayley transform is inverse to the map we've considered in the previous part. This again is an elementary manipulation with matrices, although it's a little bit more complicated. This long expression is what we get when we first apply the Cayley transform to a skew-symmetric matrix X and then the map in the other direction. In this long expression, the first factor simplifies to 2 times x plus em inverse and the whole thing inverse, and the second factor expands to 2 times x plus em inverse. Now the two 2's cancel, and that doing inverse twice is the identity, so we arrive at the expression x plus em in parentheses times x plus em inverse. Because x commutes with all the other factors, the 2 outer terms cancel and we're left with just x. This concludes the proof that one of the 2 composites is the identity. The proof that the other composite is the identity is similarly explicit. An immediate corollary is that the collapse map associated to this open embedding is an equivariant homeomorphism. The collapse map, starting from OM with its adjoint action, and then divided out, so quotient space by the ledging space, to the one-point compactification of art M. And this map sends a matrix, well, either to the inverse, that we've explicitly seen what it looks like in the proof. So it sends it to EM minus A inverse times EM plus A, if A is in OM but not in the ledging space, and to the point at infinity otherwise. This is an OM equivariant homomorphism. Where again the OM actions are by conjugation on both sides. Now I want to verify the hypothesis of the abstract splitting theorem. So I want to show that the projection map from OM with the adjoint action onto this quotient space, or we might want to go on to the one-point compactification of the adjoint representation, that this quotient map has a section in the OM equivariant stable homotopy category. This again is mostly a matter of linear algebra. It's a little bit, but not much more sophisticated. And here is how it goes. For this, we also need the vector space of symmetric matrices. So let HM be the set of all Y m by m real matrices such that Y transpose is equal to Y. So with the plus one here is a space of symmetric matrices. Symmetric m by m matrices. And then any matrix can be written as a symmetric part and an antisymmetric part uniquely. So we get that the vector space of m by m real matrices is the direct sum, the internal direct sum of the adjoint representation. These are the skew-symmetric matrices. And this HM, these are the symmetric matrices. And this is an internal direct sum decomposition as OM representations. So this is the fact that this condition of being symmetric and the condition of being skew-symmetric, both of these are invariant under conjugating by an element in the orthogonal group. The next lemma is similar but slightly different to this lemma about the Cayley transform. It will eventually give us the splitting, the map in the other direction. Now we look at the following. The map from OM cross the vector space of symmetric m by n matrices through all m by m matrices with real coefficients. The map sending a pair a comma y to a times x of minus y. This is an OM equivariant open embedding. With image the general linear group. So this x again is the familiar exponential series now done with matrices. So it's the infinite sum of 1 over n factorial by, and in this case, minus 1 to the n. I will not give the full proof, but I will explain the main ingredient. Here the first observation is that the map really has image in the general linear group, but this is clear. After all, A is invertible because it comes from the orthogonal group, and x of y times x of minus y is the identity, so x of anything is always an invertible matrix. So this clearly has image in the general linear group. What I want to explain in detail is why every element in the linear group can be written as a product in this way, and if you look at it a little bit more carefully, this will even prove that it can uniquely be written as a product in this way. So I will basically verify that this map is surjective with image, what I've claimed it is, the general linear group. So let's consider any invertible matrix, B and GLM of R. Then we can form B times B transpose. Then B transpose times B is symmetric and positive definite. In particular, it is diagonalizable with positive real eigenvalues. So BT times B is diagonalizable over R with positive real eigenvalues. And that means that we can take a square root of this. Then Z and GLM of R be the square root of BT times B. So what this means is we're going to take the matrix that has the same eigenspaces, but the eigenvalues are the positive square roots of what the eigenvalues used to be here. So in other words, a different way to say this is, so Z is diagonalizable also with positive real eigenvalues. And it satisfies that Z squared is BT times B, and this together in fact uniquely characterizes the matrix Z. Now we define our matrix A as B transpose inverse times Z, and I claim that this is in fact an orthogonal matrix, so let's do the simple calculation. So what is A times A transpose? Well, this is B transpose inverse times Z, and now the transpose of this, which is Z transpose times B inverse. But Z was symmetric, so in particular Z transpose is equal to Z, and also Z squared was B transpose times B. So we just substitute this expression and note that Z transpose is Z. So this is B transpose inverse times B transpose times B times B inverse, and this is the M by N matrices. So we conclude that A, as defined up here, is really an element of the orthogonal group. Moreover, if we multiply A with Z, well, we get B transpose inverse times Z squared, and Z squared was defined here, so this is exactly B. So we found an expression that we're looking for. We wanted to show any element in GLMR is in the image of this map. We've now written the matrix B as something from the orthogonal group, something times a matrix Z, and now we have to see that this matrix Z is of the form x minus y for a uniquely determined y. But here again, what saves us is that the matrix Z is symmetric and has positive real eigenvalues. So we can basically take a logarithm of Z. So let minus y be the logarithm of Z. And what I mean is, again, we're taking the unique matrix, which has the same eigenspaces, but the eigenvalue for minus y is the natural logarithm of what used to be the eigenvalue for Z. And then this matrix exactly has the property, if we take x in the world of matrices, we get it back. So then Z is x minus y. And altogether we've taken an arbitrary element in GL and M and written it in exactly this form, because y is again a symmetric matrix because Z was a symmetric matrix. This is all I wanted to show about the proof. Now again, we draw a corollary from this. But whenever we have an open embedding, also this one, we can do a collapse map in the opposite direction. The collapse map of this open embedding is a continuous based OM map. So it now starts from the one-point compactification here. So it starts from the sphere of the m by m matrices. But since these matrices decompose into symmetric and antisymmetric matrices, we can write this as the smash product of art m, which are the skew-symmetric matrices, and hm, which are the symmetric matrices. And we have this quotient map that sends everything that's not in the image of the open embedding to the base point at infinity, and on the image of the open embedding it's just inverse to this map. And this lands us in the one-point compactification of the left-hand side. This is already compact, this is a vector space, so the one-point compactification is OM art plus smash the sphere of HM. And now we see that we have an unstable map with the property that there is some OM representation here and here. It's the same representation. So if we go to OM spectra in the stable category, we can cancel this. Morphism of suspension spectra goes sigma infinity q. It goes from the reduced suspension spectrum of the adjoint representation smash SHM to the unreduced suspension spectrum of OM with its adjoint representation smash SM. This is a morphism of orthogonal OM spectra. And if we now apply the localization functor to the OM equivariant stable homotopy category, we can desuspend the image in OM stable homotopy category can be desuspended to a morphism. So after all, in the OM equivariant stable homotopy category, the one-point compactification of every linear representation sphere is a smash invertible object, so we can smash with the smash inverse, and this gives us a morphism sigma infinity q smash s to the minus hm, which goes from sigma infinity as at m to sigma infinity plus O of m at. So it's a morphism that exactly goes in the opposite direction of the projection map that we've discussed earlier. And what I will show starting with the next whiteboard is that this morphism really does define a section in the OM equivariant stable homotopy category. So this verifies the difficult hypothesis of the general splitting result. I would like to point out that we really have to work in the genuine stabilization of OM spaces here. because we have to be able to undo smashing with a non-trivial representation sphere here. So it would not be enough to go to the naive stabilization of OM spaces, then this would not be a smash invertible object and we couldn't make this argument. I claim that the following property holds. The morphism that I'll denote by Sm again for consistency with earlier notation. We take the suspension spectrum applied to the collapse map of this open embedding, and then we desuspend by the representation given by the symmetric matrices. This is a morphism from sigma infinity S at M to sigma infinity plus of O of M at, but it's not a point-set level morphism. This is a morphism in the OM equivariant stable homotopy category, and I claim that this is the section to the composite that we get in the other direction by first going from the unreduced suspension spectrum OM at, collapsing the mth Letching space, which gets us to the reduced suspension spectrum of OM at modulo Ln. O, and this we identified using the Calyey transform with a reduced suspension spectrum of S at M. Again, I don't want to give a full formal proof, but I want to tell you what the main ingredients are. Both of these morphisms arose from unstable constructions. In the one case, for this direction, we just directly took the suspension spectrum. For the morphism in the other direction, we had to undo the suspension with a certain representation sphere. But that means that we can also deduce this from an unstable statement, namely from the following. It suffices to show that the following composite we start with S at M smash S HM. So this is the one-point compactification of M by N matrices with OM action by conjugation. And then the quotient map to OM at plus smash SHM. And then the map induced by the Calyey transform, or rather its quotient map, smash with the identity of SHM. This gets us to S at M smash SHM, that this unstable composite is equivariantly homotopic to the identity. In the base sense, OM equivariantly homotopic to the identity. Now we recall that both of these maps were collapse maps associated with open embeddings. And collapsing along open embeddings is transitive, so if you have two open embeddings, then so is the composite, and the collapse map of the composite embedding is the composite of the two individual collapse maps. So that means that this composite is associated to a single open embedding. This composite is the collapse associated with the OM open embedding that we get by composing the previous ones. So we have to go from the M by N matrices that we can write as at M cross HM. Here we took the mth Calyey transform and the identity on HM. This gets us to OM cross HM. Here we took the other map back to M by M matrices, which sends a y to a times x of minus y. So if you work everything out, this composite sends a pair consisting of a skew symmetric matrix and a symmetric matrix. And if you look up all the definitions, it sends it to x minus em x plus em inverse times x minus y. So now you might think, well, this is a pretty complicated expression. What are we going to do with it? And it might seem for a second that maybe we are stuck here. But what will save us now is that we only have to identify the differential of this open embedding as the identity 0, 0, and then because everything is given smooth here, we can expand this map around the point 0, 0 by scaling, and then it's going to be homotopic to the linear map given by the differential at 0, 0, and this we can identify. So claim the differential at 0, 0 of this smooth embedding is 2, 1. So it's multiplication by 2 in the first summand and the identity in the second summand. And I could have modified one of the maps, the Calyey map, so it's inverse to get rid of this factor 1. That's what Crabbe actually does in his paper, but this works out just the same. Assuming this, we can scale the 2 also down to 1, and that means that the differential is equivariantly homotopic to the identity map. And that means that the whole collapse map is equivariantly homotopic to the identity. We have reduced the proof of the section property to the claim that this smooth OM equivariant embedding has the differential at 0, 0 given by multiplication by 2 in the first summand and the identity in the second summand. So let's just do this simple calculation. So to get at the differential, we have to calculate f at t times x, t times y minus f0 for t in the real numbers, and then divide by t and let t go to 0 and see what comes out. If we expand this expression and exploit that this is minus em that comes from x equals 0 being this minus sign, expanding this expression gives us tx minus em times tx plus em inverse times x minus ty, and then plus another copy of the m, that is this summand. Now, this term can be rewritten by simple algebraic manipulation. This is em minus 2 times tx plus em inverse. That's just rewriting the product of these two factors, and the rest I'm copying. X minus ty plus em. And then I'm going to do an expression modulo t squared. So I'm going to ignore all second, third, and higher powers of t. Now, if you think of t eventually being small, then identity plus something small inverse is the identity minus this, plus this squared, minus this cubed, plus this to the fourth, and so on. And I'm going to drop all the terms of squared, third power, fourth power, and so on. So modulo second and higher powers of t, this becomes em minus 2, and then it's going to be em minus tx. Also, the exponential we can evaluate modulo small powers of t. This is the identity minus t times y and then higher powers. So let's approximate also the identity up to second and higher powers of t, and then plus em. And now we just reformulate this by more simple calculations. So this is minus em, that's the difference of these two, plus 2tx times em minus ty, and then plus another copy of em. Now if we expand everything out, we'll get 2tx plus ty plus minus 2t squared xy. This again is quadratic in t, so when we pass to the limit, we can ignore it, and then what remains is this expression. If we divide it by t and let t go to 0, we exactly get the claim about the derivative. The reward of all the hard work that we've done is now the stable global splitting of the orthogonal space O that I've already written on the whiteboard in the last lecture. The corollary is there is a splitting in the global stable homotopy category as follows. The unreduced suspension spectrum of the orthogonal space made up from the orthogonal groups. We have now verified all the hypotheses that we need to apply the abstract splitting result that I reminded you of at the very beginning of this lecture. And this gives us that this is isomorphic in the global stable homotopy category to a wedge of k greater or equal to 0 of the unreduced suspension spectra of L r to the k blank smash over OK. And then the kth subquotient in the skeleton filtration. So this is OK add modulo Lk of O. But this we have also identified with the one-point compactification of the adjoint representation. So using that isomorphism, which came from the Calyey transform, we get a wedge of reduced suspension spectra of L r k blank smash over OK as of the kth adjoint representation. And this object here we had given a different name. This is the wedge over k greater or equal to 0 of the reduced suspension spectra of the global tone space over the global classifying space of the kth orthogonal group of the adjoint representation. As I mentioned a number of times already, the underlying non-equivariant splitting of this is one of the results in Miller's paper in stable splittings of Stiefel manifolds. You can now also apply the forgetful functor to an arbitrary compact Lie group, and you get a G equivariant splitting of the underlying G space of O. I have not seen this splitting anywhere in the literature before, so it might be a new result. There are a bunch of generalizations that generalize other stable splittings in Miller's paper, and I would like to at least mention them. I will not tell you very much about the proofs of these generalizations because they are very similar, slightly more general than the proofs that I have at least sketched to you in this case. The first generalization concerns the fact that we still work with R linear isometric embeddings, but we introduce an extra parameter. We define an orthogonal space O pointy brackets n by the following values. O pointy brackets n at an inner product space V is the space of linear isometric embeddings from V into Rn O plus V. So when n is equal to 0, this is just the orthogonal group of V, and the structure maps will be such that then we get the orthogonal space O back. The structure map phi lower star from O pointy brackets n at V, O pointy brackets n at W, associated with a linear isometric embedding, is again essentially given by conjugation with phi and the identity on the orthogonal complement of phi. So in formulas, this is given as follows: phi lower star of f, where f is a linear isometric embedding from V into Rn plus V, applied to a vector of the form phi of V plus W, where V is any vector in V, and W is in the orthogonal complement of phi, the image of phi, so then any vector can be uniquely written in this form. And this is just f of V, which now is not an element of W, but in R to the n plus W, and to this we add 0, W. So it's a formula that when n is equal to 0 specializes to the previous formula that we had. This already is our first example. O pointy bracket 0 is so canonically isomorphic to just O that I allow myself to write equal. The next one, O pointy brackets 1, is also particularly interesting because it models the special orthogonal groups. So here's another example. Let SO, and you are supposed to imagine that this is math boldface letters again, be the orthogonal subspace of math boldface O given by the special orthogonal groups. Let's just pause for 1 second to convince ourselves that this is really a suborthogonal space, so it's closed under the structure maps, but that's because if you have a matrix of determinant +1 and you conjugate it by anything, it still has determinant +1, and then if you add the identity, it still has determinant +1. So this is a suborthogonal space. But SO, or rather a shift of SO, is actually isomorphic to ON pointy brackets 1. How is this? The maps taking SO of R plus V, comma R plus V to linear isometric embeddings from V to R plus V that restrict an isometry with determinant +1 to the second summand to V, and then afterwards, of course, it's not going to be surjective anymore, but it's going to be a linear isometric embedding, claim that this is a homeomorphism. Why is that? Well, if you are already given a linear isometric embedding on V and you want to extend it, there's a one-dimensional additional summand that you have to define it on, but the complement of the image is also one-dimensional, so there's two unit vectors and you have to pick one of them. One of them is going to give a matrix with determinant +1 and the other one a matrix with determinant -1, and if you pick the +1, this is showing that this continuous map is bijective and everything is compact, so that is actually a homeomorphism. Moreover, these homeomorphisms for individual V's are compatible with the structure maps. So this forms an isomorphism of orthogonal spaces. Well, not quite from SO, but from what I call the shift of SO. The shift of an orthogonal space is the orthogonal space precomposed with adding a single copy of R. And this is isomorphic as an orthogonal space to O pointy brackets 1. Something that I've mentioned in a lecture a while ago when I first talked about unstable global homotopy theory is that the shift always receives a natural map from the orthogonal space, in this situation SO, that is a global equivalence. So summing this all up, we can see that the pointy bracket 1 construction in particular includes the orthogonal space made by the special orthogonal groups. So any result that we prove about O pointy brackets n, in particular for n equals 1, includes a result about the orthogonal space given by the special orthogonal groups. I'm claiming that the abstract skeleton splitting result also applies to the orthogonal spaces O pointy brackets n for all n greater equal to 0. Moreover, the arguments are generalizations of the arguments that we have seen for n equals 0, where this all specializes to the orthogonal space O. I will not give you the full proofs, but I will give you some hints of what kinds of things enter and how you have to modify the arguments. The first thing is to identify the latching object and the latching map. The latching map, which goes from Ln of O pointy brackets n to O pointy brackets n at R to the m, which is the space of linear isometric embeddings from Rm into Rn O plus Rm. And again, this is a closed embedding. And the image has a similar characterization with image those psi from Rn into Rn plus Rm such that the kernel of psi minus I2 is not 0, where I2 is the embedding as the second summand. Sending x to 0, x. An equivalent way to say this is that there has to be at least one non-zero element such that psi and this inclusion of the second summand agree on this non-zero element. Again, this map is not just a closed embedding and it's automatically OM equivariant, it's actually an OM covibration, and that means that also this orthogonal space, O pointy brackets n, is flat. The next thing is that you want a similar kind of collapse map to identify the subquotients in the skeleton filtration. And here the claim is that the following composite is an open embedding with image complement of this, so the image O pointy brackets n at Rm set theoretic complement with the mth latching space of O pointy brackets n. And the ingredients of this open embedding are all things that have already come up. So we start with a linear space, namely the space of R linear homomorphisms from R to the n into R to the m with no further conditions. Direct sum, the adjoint representation of the mth orthogonal group. We embed this into the adjoint representation of the n plus mth orthogonal group, and the embedding is as follows. We consider a linear map as a matrix, and these are matrices anyhow, so I send an f comma b to this matrix, 0, f minus f transpose b 0, and you know b was from the adjoint representation, so it's skew symmetric. Here's a 0, and this is exactly made so that the whole matrix is skew symmetric. So that actually embeds this as a On times On sub-representation of the adjoint representation of the larger group. Then here we have the Cayley transform that we've previously used, but now for index n plus n. This is an open embedding into On plus m with the adjoint representation of this larger group. And from here we can restrict to the second summand. We end in linear isometric embeddings from Rn to Rn plus Rn. So we restrict in self-isometry of Rn plus Rn to the second summand. So this is precomposing with a map that I called I2. And then the thing I leave for you to check is that this composite is an open embedding. It's also clearly OM equivariant. And for n equals 0, this just specializes to the Cayley transform, the open embedding that we've used previously. The corollary is, of course, again, that we have a collapse map. The collapse map for this embedding is an OM equivariant homomorphism from the quotient of O pointy brackets at R to the n, which is this Stiefel manifold here, modulo the mth latching space of O pointy brackets n, and it's OM equivariantly homomorphic to the sphere of the inner product space of the vector space that we have here. Now, because we're only keeping track of the O to the m action, which comes from this m and from this m, but not of the O to the n action, I can write this also as n times nu m plus ad m, where nu m is the tautological representation, OM representation on R to the m, and n times nu m is just an m-fold direct sum of copies of this. No, that's just a different way of writing this if we don't have to keep track of the action of On, but only of the action of On. The next thing to check is that also Krabbe's argument to provide the splitting, the stable splitting in the OM equivariant stable homotopy category can be generalized to this particular situation, so that you can in fact apply the general skeleton splitting result to this. If you believe this, we end up with the following theorem. There's an isomorphism in the global stable homotopy category between the unreduced suspension spectrum of O pointy brackets n and a wedge over k greater or equal to 0. And then we have the reduced suspension spectra. And now we get the global classifying space of OK and the global tone space of this, but now for this representation here. So n times nu k, because we've passed from m to k, plus at k. For n equals 0, this term goes away and we recover the previous result. An interesting special case is for n equals 1. Because for n equals 1, as we saw a little bit earlier, on the left-hand side we have the unreduced suspension spectrum, at least up to isomorphism of orthogonal spaces made from the special orthogonal groups. And this is isomorphic to the wedge of k greater or equal to 0, sigma infinity, b global O of k. And then a single copy of the natural representation and a copy of the adjoint representation. So in the stable splitting of SO, you have both of these representations, both of these infinite families of natural representations coming up, the tautological and the adjoint representation. Again, the underlying non-equivariant splitting that you get from here by applying the forgetful functor to the non-equivariant stable homotopy category is due to Miller. You can also forget to the G equivariant stable homotopy category. And when G is a non-trivial compact Lie group, I have not seen this before, so it seems to be a new result. Unfortunately, I cannot give you a reference for this yet, because the paper where I'm going to write up the proof isn't done yet. You might want to check the video description, because by the time you're watching this video, maybe the paper is ready, and if so, then you will find the link in the video description. There's yet another direction for generalization. Indeed, Miller in his topology paper, he runs the orthogonal story from the beginning in parallel with a unitary and a symplectic story, where you also have Stiefel manifolds over the complex numbers or over the quaternions. And in fact, all the arguments that I've presented here have unitary and symplectic analogues, and I want to at least mention the statements here. We define two more orthogonal spaces. One I call U, pointy brackets n, and the other one I call SP, pointy brackets n, as the orthogonal spaces with the following values. U, pointy brackets n, at a real inner product space V, is the space of linear isometric embeddings from the complexification of V into the C to the n plus the complexification of V. And similarly, SP pointy brackets n at a real inner product space V is the space of H linear isometric embeddings from the quaternification into H to the n plus V quaternified. So you're simply complexifying or quaternifying the inner product space to get a unitary or symplectic inner product space, and then you look at complex or quaternionic Stiefel manifolds as opposed to real Stiefel manifolds. The structure maps are defined in pretty much the same way as in the orthogonal situation. In this situation, all the results work out in the same way, and you get global stable splittings. There are isomorphisms in the global stable homotopy category. Generalizing Miller's non-equivariant stable splittings. The unreduced suspension spectrum of the orthogonal space U pointy brackets n decomposes as a wedge over k greater or equal to 0 of the reduced suspension spectra of the global classifying space of the kth unitary group, and then the global tone space for n times the tautological representation of UK, which is C to the k with a tautological action, direct sum the adjoint representation k, but now of the complex group. This is the adjoint representation of the kth unitary group. Similarly, the unreduced suspension spectrum of SP pointy brackets n decomposes as a wedge k greater or equal to 0, sigma infinity, the global and then the kth symplectic group. And again, a global tome space associated with a representation of this group, namely n times the tautological representation of the symplectic group with underlying vector space h to the n, direct sum the adjoint representation of the kth symplectic group, for which I write add k to the h. These two can again be described in explicit terms as skew Hermitian matrices. So if you want to define this complex in the quaternionic analog, you also have to take the complex conjugation or the quaternionic conjugation into account. They are not just the skew symmetric matrix, but the skew Hermitian matrices. Again, on underlying non-equivariant spectra, this is due to Miller, and G equivariantly for G, a non-trivial compact Lie group. I have not seen these results before. For n equals 0, this gives a stable global splitting of the unitary group, and this gives a stable global splitting of the symmetric group. And for n equals 1, here you can play the same game, and the U pointy brackets 1 is isomorphic as an orthogonal space to a shift of SU, and since shifts are globally equivalent, for n equals 1, this also gives a splitting of the unreduced suspension spectrum of the orthogonal space, the subspace of U, made by the special unitary groups. This ends today's lecture, and in fact it ends the entire course on global stable homotopy theory. I hope that I could convey some of the intrinsic beauty of the subject, and I could explain to you why global structures are useful for calculations. This ends season 1 of global homotopy theory, but it does not have to be the end of the excitement. After all, should Netflix make me a decent offer, I might consider actually producing a second season. One last time, I would like to thank you for your attention, for watching this video today, but also for sitting through the entire class with me. And always remember, act locally, but think globally.